Radioactivity and mode of decay. Nuclear chemistry is the study of the structure of atomic nuclei and the changes they undergo. Nuclear reactions, the ordinary chemical reactions discussed from the previous lessons involve changes in the outer electronic structures of atoms or molecules. In contrast, nuclear reaction result from the changes taking place within the atomic nuclei. The atomic nuclei, so this letter U is the element symbol. The number here in the upper left corner of the element symbol is the mass number and signified by letter A. Then the lower, here in the lower part of the element symbol is the atomic number and signified by Z. So let's define atomic number and mass number. Atomic number is equal to the number of protons in the nucleus. So if the atomic number is given, you can easily identify the name of the element by simply looking at the periodic table. The mass number is equal to the number of protons and neutrons in the nucleus. So if the mass number is given and you know the atomic number, so you can compute for the number of neutrons. So here we are A minus Z. So we have mass number minus the atomic number, so that is equal to N, and N is the number of neutrons in the nucleus. So nuclear equation, in a chemical reaction, we write the symbol for various chemical elements, but in a nuclear reaction, we must also explicitly indicate protons, neutrons, and electrons that are produced during the course of nuclear fission or fusion reaction. While writing the nuclear equation, we have to mention the number of protons and neutrons present in all the elements. So the following points need to be considered while writing nuclear equations. The first is a nuclear equation must be balanced. So the left side of the equation is the reactant side, and the right side of the equation is the product side. So the atomic number and the mass number in the reactant side and on the product side must be balanced. The symbol for an atom or atomic particle should include the symbol of the element, the atomic number, and the mass number. The mass number, so we defined it a while ago, and the atomic number. The mass number of an atom or of atom, which is used to describe the number of protons and neutrons, should be attached at the upper left of the symbol. The atomic number of an atom, which is used to describe the number of protons in the nucleus, should be attached at the lower left of the symbol. So for example, or examples of balanced nuclear equation. So on the left side, here are the left side is the reactant side and the right side is the product side. So here we have, so look for the atomic number and the mass number. Okay, so the mass number here is 238. Here is, we have 234 and 4, so the sum is 234 plus 4, so we have 238. So balance. 92 here, the atomic number here is 92. Here we have 90 plus 2, so 92. 92 on the product side, 92 on the reactant side. So that is balance. For letter B, we have 234 here. 234 plus 0 is still 234. 90 here, 91 plus negative 1, so we have 90. So balance, 90, 90. Letter C, 234 here. We have 230 plus 4, so we have 234, so that is balance. 91 here, 89 plus 2, that is 91, so balance. For letter D, we have 220. Here we have 216 plus 4, so that is 220. The atomic number is 86. On the product side, we have 84 plus 2, so we have 86, and so on. So, the nuclear equation must be balanced with regards to the nuclear mass or the mass number and with regards to the atomic number in the reactant side and in the product side. So let's proceed with nuclear stability. So nuclear stability is a concept that helps to identify the stability of an isotope. So the two main factors that determine nuclear stability are the neutron-proton or neutron over proton ratio and the total number of nucleons in the nucleus. So what do we mean by isotope? So isotope is an element that has the same atomic number but different atomic mass or mass number compared to the periodic table. So what are the example of isotope? For example, we have for carbon, we have three isotope for carbon. We have carbon 12, carbon 13, and we have carbon 14. So, okay. Nuclear stability refers to the tendency of a nucleus of an atom to decay, which means to change into something else. Isotopes of atoms with unstable nuclear are called radioisotopes. Radioisotopes are radioactive isotopes. Okay. Isotope stability, so the graph of stable elements is commonly referred to as the band or belt of stability. So here is the graph. Okay. The graph consists of a y-axis labeled neutrons, an x-axis labeled protons, and a nuclei. So let's see. So the x-axis it represents the number of protons, and the y-axis, it represents the number of neutrons. At the higher end or upper right of the band of stability lies the radionuclides and the decay via alpha decay. Below is positron emission or electron capture. Above is beta emission, and elements beyond the atomic number of 83 are only unstable radioactive elements. So, elements greater than or with an atomic number greater than 83 are considered unstable radioactive elements. Stable nuclei with atomic numbers up to about 20 have a neutron to proton ratio of about 1:1. So the example of that is the solid line here. Okay? So we're going to discuss later the type of decay. Okay, so here again, isotope is an element that has the same atomic number, so the atomic number of an element cannot be changed. Okay, so it is constant, but the atomic mass or can vary. Okay, so that is the what we call an isotope. Every element has a proton, neutron, and electron. The number of protons is equal to the atomic number and the number of electrons is equal the protons unless it is an ion. Okay, so to determine the number of newtons in an element, you subtract the atomic number from the atomic mass of the element. So that is discussed a while ago. Atomic mass is represented by A and atomic number is represented as Z and neutrons are represented as N. So, to know the atomic mass of an element is equal to the number of neutrons plus the number or Z, which is equal to the atomic number or equal to the number of protons. Okay, the principal factor for determining whether a nucleus is stable is the neutron to proton ratio. Elements with less than 20 atomic number are lighter and these elements nuclei and have a ratio of 1:1 and prefer to have the same amount of protons and neutrons. So here are some rules for predicting which nuclei will be most stable. Number 1, which is the neutron to proton ratio. So for example, this one, we have carbon. The mass number is 12, the atomic number is 6. Okay. Then this one, we have the nitrogen. So we have the atomic number 7 and then uh, the mass number is 14. Okay. Then oxygen, we have atomic number 8 and then the mass number is 16. So again, the mass number is equal to the number of protons plus neutron. So atomic number is equal to the number of protons. So for example here, carbon. If the atomic number is 6, so the number of protons in carbon is 6. If the mass number is equal to the proton and neutron, so if we're going to subtract 6 number of protons to this one, you will get the number of neutrons. So 12 minus 6, so we have 6. Neutron to proton ratio, so we have 6/6, so that is 1:1. Okay? So that is the same here and for oxygen. Nuclei containing more than 83 protons are unstable. So for beyond bismuth, let's see in the periodic table. So we have 83 here, 83. Okay. 83 is bismuth. So beyond bismuth, they are considered uh, unstable radioactive isotope. Okay. So number 3, nuclei with an even number of nucleons, either protons or neutrons, tend to be more stable than those with odd number of nuclear particles. Okay, so example for nuclear stability. Okay, so number 1, which isotope in each of the following pairs should be more stable? So we have silicon here. The atomic number is the same, but the mass number is different. Okay, so this one, the more stable one is the silicon, the first one. Okay, because the mass number here is 29. So here the neutron to proton ratio is 1:1. Here is not 1:1. So the answer for letter A is this one. Silicon with a mass number of 20. So for letter B, we have lithium. So the atomic number is 3 and the mass number is different. So again, the answer for letter B is the first one, the lithium with the mass number of 6 because the neutron to proton ratio here is 1:1. Next, for this problem, for each pair of element listed, predict which one has more stable isotope. So we have nickel or copper. So let's see. Okay. So the answer for letter A is nickel because nickel has an atomic number of 28, atomic number of 28 and the atomic number of copper is 29. So the if the atomic number is become larger, it become more unstable. Okay? So the answer for letter A is nickel. For letter B, we have selenium and antimony. So selenium The atomic number of selenium is 34. The atomic number of antimony is 51. So the more stable is selenium because the atomic number is only 34. Then next is cadmium and gold. Okay, so correct this one. This is not copper, so it should be gold. So cadmium, the atomic number of cadmium is 48 and the atomic number of gold is 79. So cadmium is more stable. Okay. Radioactivity. Unstable isotopes decompose or decay by a process referred as radioactivity. A few such nuclei occur in nature, accounting for natural radioactivity. Many more can be made or induced artificially by bombarding stable nuclei with high-energy particles. So we have four modes of decay or four types of decay. So we have alpha particle emission, we have beta particle emission or the beta decay, we have gamma radiation, positron emission, and we have the K electron capture. So let's proceed with the first one. So we have the alpha particle emission or alpha decay, which an ordinary helium nucleus is given up. So this one we have helium, mass number of 4 and atomic number of 2. So because this is called alpha decay, we can replace helium, the symbol of alpha here. In alpha decay, can most simply be described like this. Number one, the nucleus of an atom splits into two parts. So, for example, this one, in the reactant side, okay, we have this one. And on the product side, so the original given is split into two parts. So, the alpha particle and then uh, the other one or the other part here. Okay. One of these parts, the alpha particle, goes zooming off into space. Number 3, the nucleus left behind has its atomic number reduced by 2 and its mass number reduced by 4. So from this one, the mass number is reduced by 4 and the atomic number is reduced by 2. So the equation must be balanced both on the reactant and the product side. So we have the mass number, 222 mass number here, and here we have 4 in the helium and 218 here. 218 plus 4, so we have 222, so balance. We have 88 here, the atomic number here is 88. So 88 minus 2, we have 86. So to know the element, just find the element with atomic number of 86. So look in the periodic table. So 86, so where's 86? So this one. So radon is 86. Okay. So next we have polonium. So we have mass number of 208 and then atomic number of 84. We have helium here and then 84 minus 2, so we have 82. So look for the element with an atomic number of 82. So Pb, or that is lead. So write lead on the together with the alpha particle. Okay? So 4 plus 204, so we have 208 for the atomic mass, so balance. 84 here for the atomic number, so this one is 2 plus 82, so 84 is the total of the atomic numbers here in the product side. So that is for the alpha particle emission. The atom on the left side is the one that splits into two pieces. Number 2, one of the two atoms on the right is always an alpha particle. So we always have alpha particle here in the right side or in the on the product side. Number 3, the other atom on the right always goes down by 2 in the atomic number and 4 in the mass number. So that is the alpha particle emission or alpha decay. So, later we're going to answer this one. So, let's finish first discussing the other mode of decay. So next we have beta particle emission or the beta decay, which produces an electron given the symbol electron. So we have 0 here and -1 here for the uh, atomic number. Okay, so because this is called beta decay, so you can replace electron as the symbol of beta. In beta decay is somewhat more complex than alpha decay. This point presents a simplified view of what beta decay actually is. Number one, a neutron inside the nucleus of an atom breaks down, changing into a proton. So take note of this. A neutron inside the nucleus of an atom breaks down and changing it into a proton. Number two, it emits an electron. So the electron will be on or the beta particle will be on the product side, and an anti-neutrino which goes zooming off into space. So in the product side, we have the beta particle and the anti-neutrino. The atomic number goes up by 1 and the mass number remain unchanged. Okay, so let's look in the example here. So we have carbon here. The mass number is 14. The atomic number is 6. So write first the beta particle here, and here is the anti-neutrino. Okay. So for the anti-neutrino, the atomic number and the mass number is 0. So 0, 0. So the mass number is still the same, 14. So it doesn't change from the reactant side to the product side. Then this one, we have 0 plus -1. So -1 plus 7, so we have 6. So look for in the periodic table, the element with atomic number of 7. So let's see. So let's verify if it is nitrogen. Okay, so here is 7. So atomic element with atomic number of 7 is nitrogen. Okay. So here we have 7 plus -1 plus 0, so that is positive 6, so balance. 14 here, 14 plus 0 plus 0, so that is 14. So another example is iodine. So mass number is 131 and the atomic number is 53. So 53 here, so we have, write first the beta particle here and the anti-neutrino. 0 plus 0, so still 131 is the mass number. -1 plus 54, so that is 53. So look for in the periodic table, the element with atomic number of 54. So let's verify the element. So 54, we have this one. Okay. Xenon is the element with atomic number of 54. So the nuclei that decays is the one on the left-hand side of the equation. Number 2, the order of the nuclides on the right-hand side can be in any order. So you can write first the beta particle and the anti-neutrino followed by this one. But here, the example here is the usual way the way it should be written. Number 4, the mass number and the atomic number of the anti-neutrino are 0 and the bar above the symbol indicates it is an antiparticle. So this one, neutrino has an mass number and atomic number of 0, 0. The neutrino symbol is the Greek letter mu. So later, we're going to answer the example under beta particle. So let's continue. Gamma radiation, which consists of high energy photons, because gamma emission changes neither the mass number nor the atomic number. It is ordinarily omitted in writing nuclear equations. Gamma rays, because of their size, have the lowest ionizing power. Radioactive nuclei produced artificially in the laboratory can show alpha negative, beta negative, or gamma emission. So for this one, here is the symbol for the gamma radiation. So nothing's changed. So 6027, 6027 here. Okay. Next, we have positron emission or positron decay. A positron is identical to an electron except that it has a charge of positive 1. So, positive 1 here. Let's see in beta decay. In beta decay, we have negative 1 charge here. Okay? A positron has the symbol, this one, the electron, 0, and then positive 1. Positron decay is like a mirror image of beta decay. So, almost the same with the beta decay. Number 1, something inside the nucleus of an atom breaks down, which causes a proton to become a neutron. So, let's compare this one under beta decay. In beta decay, okay, a neutron inside the nucleus of an atom breaks down, changing it into a proton. While in positron emission, uh, the nucleus of an atom breaks down, which causes a proton to become a neutron. Number 2, it emits a positron and a neutrino, which go zooming off into space. So we have a positron and a neutrino on the product side, on the right side of the equation. Number 3, the atomic number goes down by 1 and mass number remains unchanged. So this one neutrino, so we're going to write the symbol without a bar uh, above the symbol of the neutrino. So example, we have write the positron here, the neutrino without a bar above above the symbol. So 0 plus 0 still 23, so 23. Negative 1 plus 11, so that is 12. So 12 minus 1, so that is 11. So look for the element in the periodic table with atomic number of 11, and that is so let's see. So let's verify. 20. Wait, what number is that? 11. So we have, where's the 11? Okay, here, sodium. Okay, so next is this one, manganese. Okay. So manganese with mass number of 50 and atomic number of 25. So write the positron here and the neutrino. 0 plus 0, that is 50, so 50 equal 0 plus 1 plus 24, so we have 25, so 25 here, they are balanced. So again, write first the particle, the positron, and the neutrino, and then subtract 1 from here to get the number here, and then look for the element in the periodic table with that atomic number, based on the atomic number. Okay. And last is the K electron capture, in which an electron in the innermost energy level falls into the nucleus. The result of K electron capture is the same as positron emission, where the mass number remains unchanged, and whereas atomic number is decreases by 1 unit. So, electron capture is not like any other decay. So, remember this. Alpha, beta, or positron, all other decays shoot something out of the nucleus. In electron capture, something enters the nucleus. So that is the difference between K electron capture from the other type or from the other mode of decay. So these points present a simplified view of what electron capture is. Number one, an electron from the closest energy level falls into the nucleus. So an electron falls into the nucleus which causes a proton to become a neutron. Number two, a neutrino is emitted from the nucleus. So the first one, we have electron in the nucleus. The neutrino is emitted. So the electron will be on the reactant side and neutrino will be on the product side. Number three, another electron falls into the empty energy level and so on, causing a cascade of electrons falling. One free electron moving about in space falls in the outermost empty level. The atomic number goes down by 1 and the mass number remain unchanged. So for this one, okay, so 36. Okay, here we have, okay, krypton. Okay. Atomic number of 36 and mass number of 81. So we have krypton. So we have electron here on the reactant side, and then we have neutrino on the product side. So 0 plus 81, so we have still 81 here. Negative 1 plus 36, so we have 35. So 35 plus 0, still we have 35. Then, the atomic number with 35 is this one, and that is, so let's verify. We have 35. Okay, so we have bromine. Okay. So, next is this one, 239 plus 0. So, still 239. So, 239 here, then 0, 239. So, balance. 96 plus negative 1. So, we have 95. Then, 95 plus 0 here is 95. So, that is balance. So, that is the, this is different from the other mode of decay. From the other mode of decay, common, we're adding on the, we're adding something on the uh, product side. Here, we have here electron in the reactant side and neutrino on the product side. So let's proceed with the examples. Okay, so let's proceed with the alpha particle emission example. Write the alpha decay equation for these 5 nuclides. Okay. So here's the answer. So the first step for alpha particle is to alpha particle emission is to write the alpha particle on the right side of the equation. Subtract 4 from the mass number here. So 256 minus 4, so we have 252 here. 2 minus 103, so that is 101. Then find the element with atomic number of 101 in the periodic table. So 101, so that is here, so that is mendelevium. Okay, so that is the answer for number 1. For number 2, we have 4 minus 231, so that is 227. 2 minus 91, so we have 89 here. So the element with atomic number of 89, so that is, okay, verse 89. So this one, so actinium. So that is the answer for number 2. Next, for number 3, we have 4 minus 225, so we have 221 here. Then 2 minus 89, so we have 87. And the element with atomic number of 87 is, where's 87? This one, so that is francium. So that is the answer for number 3. Number 4, we have uh, so this one, the helium or the alpha particle can be in any order. So you can write the alpha particle here or here. So it doesn't matter. So 4 minus 211, so that is 207. 2 minus 87, so that is 85. So the element with atomic number of 85, so that is astatine. So this one, astatine. So the periodic table of elements can be found on your canvas. Okay. So here, number 5, the last number for alpha particle emission example. So we have 4 minus 185, so that is 181. 2 minus 79, so we have 77. So the atomic number with 77, the element with atomic number of 77 is, okay, iridium. So that is for alpha particle emission or alpha decay. So remember that this one is the alpha particle. So next, let's proceed with beta particle. So write out the full beta decay equation. So for these 5. So here's the answer. So under beta particle emission, we have the beta particle here and the antineutrino here. 0 plus 0, so still, so this one is 6. Negative 1, so plus 1, because when you transfer negative 1 on the other side of the equation, so that will be positive 1. So 2 plus 1, so we have 3 here. So the element with uh, atomic number of 3, so that is the lithium. Okay, so let's verify. So this one is 3 lithium here. And next, we have this one, 0 plus 0, so we have 24 here, 24 here. Then negative 1 plus 11, so that is 12. So the element with atomic number of 12, so that is this one, magnesium. Okay. Next, problem number 3. We have 0 plus 0, so that is 201. Negative 1 plus 79, 1 plus 79, so we have 80. So the element with atomic number of 80 is mercury. Okay. Then next, number 4. So we have 52 here, 52. Then negative 1, 1 plus 26, so we have 27. And the element with atomic number of 27 is cobalt. Then for the last number, we have 0, 0 here plus 42. So we have 42 here, 42 here. So that is balance. 0 plus negative 1, so negative 1, so we have 1 plus 19, so we have 20. The element with atomic number of 20 is calcium. So remember, under beta particle, we have electron here in the product side and an antineutrino. So you can check your answer by uh, adding the or finding the total of the mass number and the sum of the atomic number here. So they should be balanced. So let's proceed with okay. So that is for the mode of decay. rate of radioactive decay, and age of organic material. So alpha particles are made of two protons and two neutrons. So this means that they have a charge of positive 2 and a mass of 4. The mass is measured in atomic mass units or AMU, where each proton and neutron is equal to 1. We can write them as, from the previous lesson, this one. So we use alpha particle here, or we can use helium because they are or they have the same or they are the same as helium nucleus. So we can change alpha here with helium. Alpha particles are relatively slow and heavy. They have a low penetrating power. You can stop them with just a sheet of paper. Because they have a large charge, alpha particles ionize or pull electrons from the atoms strongly. Next, we have the beta particles. Beta particles have a charge of -1 and a mass of about 1 over 2000 of a proton. This means that the beta particles are the same as an electron. We can write them as B negative or because they are the same as electron written in isotope. So this is the beta particle. So you can change the beta here, use the symbol for electron. They are fast and light. Beta particles have a medium penetrating power. They are stopped by a sheet of aluminum or plastics. Beta particles ionize atoms that they pass but not as strongly as alpha particles do. Gamma rays are waves, not particles. So take note of this. This means that they have no mass and no charge. So we sometimes write gamma waves as this is the symbol for gamma. So we have 0, 0 here. So gamma rays have high penetrating power. It takes a thick sheet of metal such as lead or concrete to reduce them significantly. Gamma rays do not directly ionize other atoms, although they may cause atoms to emit other particles, which will then cause ionization. We don't find pure gamma sources. Gamma rays are emitted alongside alpha or beta particles. Strictly speaking, gamma emission isn't radioactive decay because it doesn't change the state of the nucleus, it just carries away some energy. So these one particles that ionize other atoms strongly have a low penetrating power because they lose energy each time they ionize an atom. Therefore, alpha particles are easy to stop and gamma rays are hard to stop. Let's proceed with the rate of radioactive decay. So, in any sample of a given radioactive substance, the number of atoms of the radioactive isotope must decrease with time as their nuclei decay or decompose to nuclei of a more stable isotope. Using N, so N represent the number of atoms of the radioactive isotope, the number of radioactive nuclei present. We can define the rate of decay of the sample, which is also called activity or represented by capital letter A, as the decrease or disintegration in the number of the radioisotopes nuclei per unit of time. Radioactive or radioactive decay is the emission of a particle or a photon that results from the spontaneous decomposition of the unstable nucleus of an atom. The rate of radioactive decay is an intrinsic property of each radioactive isotope that is independent of the chemical and the physical form of the radioactive isotope. The rate is also independent of temperature. So again, activity is usually measured in disintegration or disintegration per second or DPS or disintegration per minute, so DPM. Uh, Again, activity is the decrease in the number of radioisotopes nuclei per unit of time. So the common unit of time is sometimes we use per second, per year, or per day, per month, okay, and even per hour. The activity of a sample is directly proportional to the number of atoms of the radioactive isotope in the sample. So activity is directly proportional to the number of atoms of the radioactive isotope. So what is K here? So this is the formula in computing the activity. So if you're going to find the N, the number of uh, and the number of atoms of the radioactive isotope. So the formula is cross multiply or divide both side by K. So that is A over K, activity over K. So if you're going to find K, that is A over N. So what is K? K is the first order rate constant, which has a unit of inverse of time. Example, we have s raised to negative 1, year raised to negative 1. So, inverse of time. So, it can be minute raised to negative 1, and so on. And a characteristic value for each radioactive isotope. What is first order reaction? The rate of a first order reaction is proportional to the concentration of one reactant. Okay? A common example of a first order reaction is radioactive decay, the spontaneous process through which an unstable atomic nucleus breaks into smaller and more stable fragments. So this one, we have ln x sub O over x is equal to kT, where x is the amount of the radioactive species present at time t, and x sub O is the amount of the radioactive species present at time 0. Meaning x sub O is the initial amount, and then x is the amount at a given time t. So, the SI unit for measurement of activity can be expressed in terms of the number of atoms per decaying or per atoms decaying per second, or atoms per second, or that is at 1 atom per second, that is equal to 1 becquerel, and 1 becquerel or 1 capital B, and then we have small letter q is the symbol we use for becquerel. 1 becquerel is equal to 1 decay per second, or that is equal to 1 atom per second. Okay? Another unit of activity is Curie, and represented by capital C, then we have I. In 1 Curie, we have 3.7 times 10 raised to 10 becquerels, or decays per second, or atoms per second. So take note of the two unit as a unit for measurement of activity. Next, we have this one. K is equal to ln 2 over T sa T 1 half. T 1 half here is the half-life of a given substance. Okay? So the half-life means half of its life is the amount of time it takes for half of the nuclei in a sample to decay. For a given number of atoms, isotopes with shorter half-lives, half-life decays more rapidly, undergoing a greater number of radioactive decays per unit time than do isotopes with longer half-lives. Let's go back here. So where do we get this formula? So we get this formula based on this formula. So we'll have ln x sub O over x is equal to kT. So let's derive the formula. So for example, this one, okay, okay, so we have ln x sub O. X sub O is the initial amount. So, for example, we have the initial amount of the whole uh, amount of the substance. So, that represents 1. Okay? And then, X is the present amount at time t. So, at the present time, where the amount becomes half of the original. So, let's write 1/2 here. Okay, that's 1/2. And then we have equal to kt. K, and then t is 1/2 because that is where the time where the original amount become half of the original. Okay, so for this one, you can 1 divided by 1/2, so that is equal to 2. So we have ln 2 here. So that's mean in 1, how many 1/2 do we have? So that is 2. So we have ln 2 is equal to kt. Okay, kt, and then we have 1/2. So if we're going to compute for the half-life, okay, divide both side by k. So the formula will become, okay, let's go back here. K is equal to ln 2 over the half-life. Okay, so based from this formula, we get this formula for the if you're going to compute, or if you're going to compute for K, this is the formula. If you're going to compute for the half-life, cross multiply, so this will become T 1/2 equal to ln 2 over K. So half-lives and application of some radioactive isotopes. So this one, the common radioactive isotope is the carbon-14. So, you must remember the half-life of that. So, that is 5.7 times 10 raised to 3 year. So, typical uses for carbon-14 is dating of artifacts. Okay? And just read the other examples. Okay? So, here's another page for the some of the example of radioactive isotopes and their half-lives and their applications. Okay. Okay. Age of organic material. So radioisotope dating techniques. In our earlier discussion, we used the half-life of a first-order reaction to calculate how long the reaction had been occurring. Because nuclear decay reactions follow first-order kinetics and have a rate constant that is independent of temperature and the chemical and or physical environment, we can perform similar calculation using the half-lives of isotopes to estimate the ages of geological and archaeological artifacts. The techniques that have been developed for this application are known as the radioisotope dating techniques. So the most common is the carbon-14 dating. So the most common method for measuring the age of ancient object is the carbon-14 dating. Radiocarbon dating is a method that provides object age estimate for a carbon-based materials that originated from living organism. An age could be estimated by measuring the amount of carbon-14 present in the sample and comparing this against the internationally used reference standard. So let's proceed with examples under rate of radioactive decay and age of organic material. Example number 1, the half-life of radium-226 is 1.6 times 10 raised to 3 years. Letter A, calculate K in S raised to negative 1. Letter B, what is the activity in curies of 1 gram sample of Ra226? Letter C, what is the mass in grams of a sample of Ra226 that has an activity of 1 times 10 raised to 9 atoms per minute? So, let's proceed with letter A. So, for letter A, the half-life is given. So, the half-life of radium-226 is 1.60 times 10 raised to 3 years. And for letter A, we're we're asked to find K in S raised to negative 1. So, therefore, the unit of time must be in second. So, the formula we're going to use is this one. So, ln 2 over 2 or ln 2 over the half-life. So, this is direct substitution, but we have to convert the years into second. So, 1.60 times 10 raised to 3 years times in 1 year, we have 365 days, so the year will be cancelled out. And in 1 day, we have 24 hours, so cancel the days here and the day here. Times, in 1 hour, we have 60 minutes, so cancel the hour. And in 1 minute, we have 60 seconds, so cancel the minute, so the unit will be in seconds. So if you're going to multiply this, you will get 5 or approximately equal to 5.05 times 10 raised to 10 seconds. So that is the half-life of Ra226 in seconds. So substitute the half-life in the equation. So we have ln 2 over 5.05 times 10 raised to 10 seconds, and you will get approximately 1.37 times 10 raised to negative 11 s raised to negative 1, or that is the same as 1.37 times 10 raised to negative 11 per second. So that is for letter A. So we're going to use that K in the next letter. So for letter B, what is the activity in curies of 1 gram sample of Ra226? So we're asked to find the activity in curies of 1 gram sample of Ra226. So the formula for the activity is equal to Kn. So we already solved for the K, so we need to solve for N. N is the number of atoms, okay? Uh, but we're being asked, we have to convert the number of atoms into, uh, this one, the given is 1 gram sample, so we have to convert it into number of atoms. So we have in 1 gram of Ra, okay, times, okay, in 1 gram of radium, we have 1 mole. In 1 mole of radium, we have 6.022 times 10 raised to 23 atoms. So this is the Avogadro's number. You can use your calculator to have that constant. So for those who are using Casio 991 ES Plus or 991 ES, just go to constant, uh, that is constant 24. Okay? So then next, in 1 mole of Ra, we have 226 grams of Ra. So cancel the grams of Ra here, cancel the mole of Ra here, so the unit will become atoms. So in 1 gram of radium, we have 2.6646 times 10 raised to 21 atoms. So substitute the value, so this one is the value of K. So we solve this one in letter A. So we have 1.37 times 10 raised to negative 11 per second. And then N is equal to 10.6646 times 10 raised to 21 atoms. And you will get approximately equal to 3.6505 times 10 raised to 10 atoms per second. Or 1 atom per second, that is atoms per second is equal to becquerel. So you can write also your answer as 3.6505 times 10 raised to 10 becquerels. But we're being asked the activity in curie. So 3.6505 times 10 raised to 10 becquerel. In 1 curie, we have 3.7 times 10 raised to 10 becquerels. So cancel the becquerels here. So the unit will be in curie. So approximately, we have 0.9866 curie or 0.99 curie. So that is the answer for letter B. And next, for letter C, what is the mass in gram of a sample of Ra226 that has an activity of 1 times 10 raised to 9 atoms per minute? So given uh, the activity is given and we're being asked for the mass in grams of Ra226. So we have for letter C, A is equal to Kn. So N is the number of atoms and N is equal to A over K. We're going to find the number of atoms and convert the number of or the atoms in grams. So the reverse process of what we did from the previous letter. So letter A, we have the activity given is 1 times 10 raised to 9 atoms per minute. Convert first the atoms per minute to atoms per second. So in 1 minute, we have 60 seconds. So cancel the minutes. So the unit will become atoms per second. And this is approximately equal to 1.67 times 10 raised to 7 atoms per second. So we have the value of A, and then K is the value of K we have is 1.37 times 10 raised to negative 11 per second. And then substitute here the value of A, which is 1.67 times 10 raised to 7 atoms per second. So divide this. So we will get or multiply this one, okay, to the reciprocal of the denominator, or multiply the numerator by the reciprocal of the denominator. So cancel the second. So 1.67 divided by 1.37 times 10 raised to negative 11. So that is approximately equal to 1.2190 times 10 raised to 18 atoms. So, okay, atoms. So, na atoms, we're going to convert atoms into grams. So, in 1.2190 times 10 raised to 18 atoms, in 1 mole, we have the Avogadro's number. So, we have 6.022 times 10 raised to 23 atoms. So, cancel the atoms. And we have to cancel out mole. In 1 mole of radium, we have 226 grams of radium. So cancel the mole here, and the unit will become grams of radium. So the answer, if you're going to evaluate this one, approximately you will get 4.57 times 10 raised to negative 4 grams of radium. Okay, and that is the answer for letter N. So, in atoms, that is 1.2190 times 10 raised to 18 atoms. In grams of radium, that is 4.57 times 10 raised to negative 4. So, that is the answer for number 1. So, let's proceed number 2. Krypton 87 has a rate constant of 1.5 times 10 raised to negative 4 per second. So, this is the value of K. What is the activity of a 2 milligram sample? So the given is we have what is the activity. So A is equal to Kn, and then we the value, okay, for 2 milligrams. Okay, so convert 2 milligrams. 2 milligram, milli that is the same as 2 times 10 raised to negative 3 grams. Okay, milli is times 10 raised to negative 3. We have to convert milligrams into atoms. So, in 1 mole of krypton, we have 6.022 times 10 raised to 23 atoms. So, times 1, in 1 mole of, please correct this one, it should be krypton. Okay, so in 1 mole of krypton, we have 87 grams of krypton. So, cancel the mole of krypton and then cancel the gram here. So, the remaining unit will be atoms. So, approximately, you will get 1.3844 times 10 raised to 19 atoms. So, substitute K given is the K given is 1.5 times 10 raised to negative 4 per second. And then this one, 1.3844 times 10 raised to 19 atoms. So approximately that is equal to 2.0766 times 10 raised to 15 atoms per second. Or 2.0766 times 10 raised to 15 becquerels. So if you're going to convert becquerel in curie, multiply this one to 1 over 3.7 times 10 raised to 10 becquerel. So becquerels will be cancelled out. So the unit will be curie, and that is approximately equal to 56,124.32 curie. So this is the answer for problem number 2. 2.0766 times 10 raised to 15 atoms per second, or becquerel, or approximately equal to 56,124.32 curie. So let's proceed with problem number 3. The half-life of zinc 71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes has elapsed? So the half-life of zinc 71 is given, so that is 2.4 minutes. Initially, at time equal to 0, the original amount is 100 grams. After 7.2 minutes, we're asked how many or how much of the original is left, okay? Or how many grams uh, is left after 7.2 minutes. So, we can use the formula ln x sub o over x because we have the initial amount, initial time, and then the after the value of t here, and we're being asked for the present amount. So, we can use the formula ln x sub o over x is equal to kt here. We have x sub o. X is unknown. We have the half-life, but we don't have the K. The formula for K is equal to ln 2 divided by the half-life. So we have ln 2 divided by 2.4 minute. So that is approximately equal to 0.2888 per minute. So we have the value of K here. So this one, ln x sub o over x is equal to kt. So you can apply the property of logarithm here. So division, that is subtraction. If this is x sub o multiplied to x, this will become ln x sub o plus ln x. So recall the properties of logarithm. So this will become ln x sub o minus ln x is equal to kt. Then uh, transpose ln x on the right side. So that will become positive ln x. So here, positive ln x. Transpose kt on the left side. So that will become minus kt. So that is ln x sub o minus kt. So we're being asked for x. So to eliminate ln, recall that, okay, so this one, for e raised to ln x. For e raised to ln x, we can rewrite or recall the again the property of logarithm and exponential function. So we have ln e raised to ln x. Okay? We can write e raised to ln x as e, okay, e raised to log base e of x. Okay? Under property of logarithm, okay, so if this is the same with this, okay, that will be cancelled out, so the remaining value will be this one. So that will be equal to x. Okay. So let's go back here. Okay, so this one will become x. And here, we can write also this one as, let's proceed with the next page. This one, um, multiplication of same base, we're going to add the exponent. Division of same base, we're going to subtract the exponent. So, because here we have subtraction, meaning we can write this one also as this one. E raised to ln x sub o over e raised to kt. Because division of same base, we're going to subtract the exponent. So that is ln x sub o minus kt. So that is the previous equation here. Then simplify again this one. The same way we simplify this one, e raised to ln x. So ln here will become log base e. So uh, that will be equal to x sub o. So x is equal to x sub o over e raised to kt. X sub o, that is equal to 100. E raised to kt. K is 0.288 per minute. And then t is 7.2 minutes. Okay. So evaluate this one. We're going to have 12.50 grams. So that is after 7.2 minutes, the present 12.50 grams of zinc 71 will be left after 7.2 minutes has elapsed. So that is the answer for problem number 3. Okay. Mass energy relations and nuclear binding energy. The relationship between mass and energy is expressed in the following equation. So we have equation number 1, E is equal to mc squared, where c is the speed of light, equal to 2.998 times 10 raised to 8 meter per seconds, or approximately equal to 3 times 10 raised to 8 meter per seconds. So E is expressed in unit of joules and m in kilograms. So the unit of E or energy is joules and the unit of mass is in kilogram. And C is in meter per seconds. Albert Einstein first derived this relationship in 1905 as part of his special theory of relativity. The mass of a particle is directly proportional to its energy, meaning, according to equation number 1 or based from equation number 1, every mass has an associated energy. And similarly, any reaction that involves a change in energy must be accompanied by a change in mass. This implies that all exothermic reactions should be accompanied by decrease in mass, and all endothermic reactions should be accompanied by increase in mass. The energy change accompanying a nuclear reaction can be calculated from based from the first equation, E is equal to mc squared. So for every change in mass, there is equivalent change in energy. So we have delta E is equal to c squared multiplied to delta m. Delta m equal to the change in mass, which is equal to the mass of the products minus mass of the reactants. Delta E is equal to the energy of the products minus energy of the reactants. And c, again, that is equal to the speed of light, and that is constant. In a spontaneous nuclear reaction, the product weighs less than the reactant. So delta M is negative. In this case, the energy of the products is less than that of the reactant, so delta E will be negative. And energy is evolved to the surroundings. The change in mass, or delta M, can readily be calculated from a table of nuclear masses. So you can see uh, the file nuclear masses.pdf. So this one, okay. So this is the example of the nuclear masses table, okay. Okay. So here you will see the element, the atomic number, its mass number, and the atomic mass. Okay, in atomic mass, and another, this is the continuation. So look for nuclear masses .pdf. The unified mass unit, or Dalton, the symbol for that is U, or dA, or AMU, or atomic mass unit, is a standard unit of mass that quantifies mass on an atomic or molecular scale, or atomic mass. So one unified atomic mass, or one unified atomic mass unit, is approximately the mass of one nucleon, either a single proton or neutron, and is numerically equivalent to 1 gram per mole. So 1 AMU is equal to 1 gram per mole. So for the electron, the symbol for electron is this one. Electrical charge is negative 1. The atomic mass of electron, or the mass in our AMU, that is equal to 0.000549. So this one can be computed using your calculator. Given the mass of your calculator, so I'm using Casio 991 ES Plus. So the mass of the electron is constant 0.3. Okay, so press constant 0.3. So ME, so that is equal to approximately 9.11 times 10 raised to negative 31 kilogram. So convert kilogram to gram. So multiply this one by the mass in kilogram into by 1,000, because you're going to convert kilogram to gram. Uh, we have 1,000 gram for every 1 kilogram. Okay? And then multiply it by the Avogadro's number. So that is constant 24. Okay. And you will get 5.49 times 10 raised to negative 4. So that is 0.00549. So the same process with proton and neutron. Proton, based on Casio 991 ES Plus. So the mass of proton is constant 0.1. The mass of neutron is constant 0.2. Okay, so you will get this one. Okay, so you don't need to memorize the this one. Okay. To obtain a more useful form of the equation, delta E is equal to c squared delta m. Substitute for c its value in meters per second. So if we're going to substitute c here, so we have c squared. So c squared, so we have 3 times 10 raised to 8 quantity squared. So that will become 9 times 10 raised to 16. So the unit will be squared also. So that it will become meter squared per second squared. Then we have delta M here. So the unit of energy is joule. So we have 1 joule here. The unit of, we have, if we're going to use this formula, the unit of mass is in kilograms, so we have 1 kilogram. And then c squared, we have meter per second, then quantity squared, so we have meter squared per second squared. So if divide both side by kilogram, so the kilogram here will be cancelled out. So we have 1 joule per kilogram here, and then 1 meter squared per second squared. So the meter squared per second squared here can be written as joule per kilogram. So instead of writing meter squared per second squared, since 1 meter squared per second squared is equal to 1 joule per kilogram, this one will become 9 times 10 raised to 16 joule per kilogram instead of writing meter squared per second squared. And then just copy delta M. So this is the first equation. Okay? So another equation for delta E. So we have delta E is equal to 9 times 10 raised to 16 joule per kilogram multiply to delta M. So we can convert also this one if we want, instead of joule, we want it to convert it to kilojoule, and then we want kilogram to convert it into gram. So this one, okay. So to convert joule to kilojoule, so this one, okay. In 1 kilojoule, we have 1,000 joule. Okay. So joule here will be cancelled out. So we have kilojoule here. Then if you're going to convert kilogram to gram, so in 1 kilogram, we have 1,000 gram. Okay, so cancel out kilogram, cancel out joule. So the unit will be kilojoule per gram. So multiply this equation and you will get uh, 9 times 10 raised to 10. Instead of joule per kilogram, we have kilojoule per gram, and then multiply to delta M. So common uh, from our examples, we will be discussing 3 examples for this. We're going to use this equation. Okay, so delta E is equal to 9 times 10 raised to 10 kilojoule per gram multiplied to delta M. The joule is a unit of energy in the SI system. Energy is measured in joules. However, joule is a very large unit while dealing with electrons and other tiny particles. Hence, electron volt is used while dealing with smaller particles like electrons. Electron volt is defined as the amount of energy one electron gains by moving through a potential difference of 1 volt. Hence, 1 electron volt is equal to elementary charge 1 point or approximately 1.60 times 10 raised to negative 19 coulombs multiplied by 1 volt. So 1 electron volt is equal to 1.60 times 10 raised to negative 19 coulomb multiplied to 1 volt, or 1 electron volt is equal to 1.60 or 602 times 10 raised to negative 19 joule. So we're going to use this conversion later in example number 3 for mass energy relation. Okay, so let's proceed with example number 1. Example number 1, for the radioactive decay of radium, so we have radium-226 here. So calculate the delta E in kilojoules when 10.2 grams radium decays. So we have the equation. So given the equation, so radium-222 undergo alpha decay. Okay, because we have alpha particle here in the product side. So, to compute for the delta E, we have to find first the delta M. So, let's proceed with the solution. Okay. So, use the table of nuclear masses to find the nuclear masses and delta M for the decay of 1 mole of Ra226. So, again, take note, do not round off the nuclear masses. So, write the whole number as it is. Okay? So, delta M is equal to nuclear masses of the product minus nuclear masses of the reactant. So, mass of 1 mole of this one, we have 1 mole here, 1 mole here, and then we have 1 mole here. So, mass of 1 mole of first masses of the product. So, let's see helium and radon. Mass of 1 mole of helium-4, this is the mass number. Then, this is the atomic number. Mass number, atomic number, mass number, then atomic number. So, plus mass of 1 mole of radon-222. Then, take note this one, it should be 222. Minus, then, the mass of 1 mole radium-226. So, for helium-4 with atomic number of 2, okay, so let's see in the nuclear masses table. Helium, atomic number of 2 and then mass number of 4. So, this one, we're going to use this one. 4.00150. Then, for radon, we have 80, radon Rn86. We have atomic number of 86, then mass number of 222. So, we're going to use 221.9703. And then for radium, we're going this one. The value is 225.9771. Again, do not round it off. So, the value will be this one. Add 4.00150 plus 221.9703. Then, subtract. Okay, so minus 225.9771 grams. So, you will get negative 0.0053 grams per 1 mole of Ra226. But the question is, calculate the delta E in kilograms when 10.2 grams radium decays. So, the computed value for what we compute here, delta M, is for 1 mole of Ra226, not for 10.2 grams. So, we have to compute for delta M for 10.2 grams of Ra226. So, 10.2 grams Ra. So, in 1 mole of radium, we have 226 grams. Then, multiply to this one, negative 0.0053 grams per 1 mole of Ra. Grams of Ra cancelled out, mole of Ra cancelled out. So, the unit will be in grams. So, we have delta M is equal to negative 2.39 times 10 raised to negative 4 grams. So, that will be the change in mass for a 10.2 grams radium. Okay. So, next, we're going to find the delta E. Delta E, the formula we're going to use is the 9 times 10 raised to 10 kilojoule per gram delta M, since delta M is in grams. So, 9 times 10 raised to 10, then the value of delta M here is negative 2.39 times 10 raised to negative 4 grams. So, cancel out the grams, so the unit will be in kilojoules. So, you will get approximately equal to negative 2.15 times 10 raised to 7 kilojoule. So, that is the answer for problem number 1. So, let's proceed with problem number 2. Strontium-90 is a dangerous byproduct of atomic testing because it mimics the action of calcium in the body. It decays in 2 beta emissions to give zirconium-90. The nuclear mass is given. We have 89.8824 AMU. So, take note, for letter A, write a balanced nuclear equation for the overall decay of strontium-90. So, strontium-90, given this one is the the mass number, okay? The atomic number can be found using the periodic table. So this will be the equation since it's in the problem, it says that it decays in 2 beta emission. So the two beta emission will be on the product side and zirconium 90 will be on the product side also. Okay? Strontium 90, the atomic number of that is 38. So see on the periodic table. Then this one, 2 beta emission. So you can write E here or the beta symbol, okay? Or beta here. So, this one naman, we have zirconium 90. The atomic number is 40. So, for letter B, calculate delta M in grams when 1 mole of strontium 90 decays to zirconium 90. So, delta M, again, mass of the product minus mass of the reactant. So, this one, based on the table, okay, we have 0.0055 here, okay. So, because we have 2 moles here, or 2 beta particle here, so we have to multiply it by 2. Then, zirconium 90, we have zirconium 90 given on the problem. Okay, so we have 89.8824. Okay, so gram per 1 mole of zirconium 90. Then minus strontium 90. Based on the table, we have strontium 90. So where's strontium 90? Okay, this one, 89.8869. Okay. Then 2 times 0.000055 plus 89.8824, then quantity minus 89.8869, you will get negative 0.0034 grams per 1 mole of strontium 90. So, compute delta M for 1 gram. Okay, so we have 1 gram of strontium here. Multiply by 1 mole strontium. We have the SR90, so we have 90 grams here. Multiply to negative 0.0034 grams per 1 mole of strontium. So, cancel this one. So, the remaining unit will be the gram. So, we have negative 3.78 times 10 raised to negative 5 grams. Then, for letter C, how much energy in kilojoules is given off by the decay of 6.50 milligrams of strontium 90? For letter B, delta M for 1 gram. For letter C, how much energy? So, we're going to compute for the delta E by the decay of 6.50 milligrams of strontium 90. So, compute first delta M for 6.5 milligrams. So, we have 6.50 times 10 raised to negative 3 because of the prefix milli. Okay? Times 1 mole strontium over 90 grams SR here. So, cancel this out. Then, multiply to negative 0.0034 grams per 1 mole of strontium here. So, cancel out this one. And you will get negative 2.456 times 10 raised to negative 7 grams. Then, for delta E is equal to, since we're looking for the energy in kilojoules, so we're going to use this formula, 9 times 10 raised to 10 kilojoule per gram. Multiply to the delta M for 6.5 milligram, we have negative 2.456 times 10 raised to negative 7 grams. So, cancel the gram here. So, the remaining unit will be kilojoule. So you will get approximately equal to negative 2.21 times 10 raised to 4 kilojoule. So if your answer is very small, you can express it into scientific notation. If your answer is very large number, you can express it in scientific notation. Okay? So that is problem number 2. So let's proceed to problem number 3. Calculate the changes in mass, okay, change delta M in atomic mass unit and energy in kilojoules per mole and kilo electron volts per atom that accompany the radioactive decay of tritium. Tritium is hydrogen 3 to helium-3 and a beta particle. So, for the radioactive decay of tritium, in the product side, we have the helium or uh, we have helium and then we have helium-3 and then beta particle. So, the equation will be this one. Hydrogen, we have hydrogen 3, then the atomic number of hydrogen is 1. So, look for the atomic number on the periodic table. We have helium-3 here, then the atomic number of helium is 2. Then we have beta particle, so we have this one. So, you can change E, you can use beta here. So, mass of the product minus mass of the reactant. So for the for the helium 3, so we have helium 3, okay? Helium 3, this one, 3.01493. Okay? 3.01493. Okay? Then plus for the beta particle, we have 0.0055. Then quantity minus for hydrogen 3, we have, okay, for hydrogen 3, okay, this one, hydrogen 3, 3.01550. Okay, and you will get negative 2 times 10 raised to negative 5 grams per mole of tritium. Or you can write AMU because 1 gram per mole is equal to AMU. Then, we are asked to find the energy in kilojoules per mole and kilo electron volts per atom. So, solving for delta E, we have 9 times 10 raised to 10 kilojoules per gram, then negative 2 times 10 raised to negative 5. Then this one, we have grams per mole, so cancel the gram here. So, we have kilojoule per mole. So, the answer is negative 1.8 or approximately equal to negative 1.8 times 10 raised to 6 kilojoule per mole. So that is for kilojoule per mole. Next, we're going to solve for the energy in kilo electron volts per atom. Okay? So, convert kilojoules to kilo electron volt. So, we're going to use this relationship that 1 electron volt is equal to 1.6. We're going to use 1.6022 times 10 raised to negative 19 joule. First, convert kilojoule to joule. So, in 1 kilojoule, we have 1,000 joules. So, kilojoule here will be cancelled out. Then, convert joule to electron volt. So, in 1 electron volt, we have 6.02 times 10 raised to negative 19 joule here. Then, converting electron volt to kilo electron volt. So, for every 1 kilo electron volt, we have 1,000 electron volt. So, cancel EV here. Then, we're okay for electron volt. How about for mole? In 1 mole, we have 6.022 times 10 raised to 23 atoms. So, the unit will be in kilo electron volt per atom. So, the answer is negative 18.66 kilo electron volt per atom. So that is for problem number 3. Okay, so let's proceed with the nuclear binding energy. Nuclei are made up of protons and neutrons, but the mass of a nucleus is always less than the sum of the individual masses of the protons and neutrons which constitute it. The difference is a measure of the nuclear binding energy which hold the nucleus together. This binding energy can be calculated from the Einstein relationship delta E is equal to C squared delta M. Consider the lithium-6, okay, nucleus, which contains 3 protons and 3 neutrons. So why 3 protons and 3 neutrons? The atomic number is equal to the number of protons. So we have 3 protons here. The mass number is equal to the number of neutrons and protons. So if we have 3 protons, 6 minus 3 proton, so the remaining number will be the number of neutrons. So we have 3 neutrons and 3 protons. So according to table 18.4, so table 18.4 is the table of nuclear masses. 1 mole of lithium-6 nuclei weighs 6.01348 grams. So let's verify the nuclear mass of lithium-6. Okay. So lithium-6, this one, 6.01348. Okay. In contrast, the total mass of 3 moles of neutrons and 3 moles of proton is, for 3 moles of neutrons, so for neutron, we have, okay, this one, we have 1.00867, and for proton, we're going to use 1.00, this one, we're going to use H1, 1.00728, okay? So since we have 3 protons and 3 neutrons, we're going to multiply their nuclear masses by the number of neutrons and the number of protons. So we have 3 times 1.00867 here, then plus 3 times 1.00728. So that is equal to 6.04785 grams. So comparing the masses, so lithium-6 is equal to 6.01348 and this one is 6.04785. So this is bigger compared to the nuclear mass of lithium-6. So clearly, 1 mole of lithium-6 weigh less than the corresponding protons and neutrons. For the process, so this is the equation. So we have lithium-6 here. This one is the atomic number. This is the symbol we're going to use for the proton. So we have positive 1 here. So we have 3 here because we have 3 proton and 3 neutron. Neutron, we have positive 1 here and 0 here. Then multiply 2, 3. So this is the equation. Okay. So for that, delta M is equal to 6.04785 minus 6.01348 grams. So that is equal to 0.03437 gram per 1 mole of lithium. So the change in mass is what we call the mass defect. Okay? So in physics and chemistry, mass defect refers to the difference in mass between an atom and the sum of the masses of the protons and neutrons and electrons of the atom. So that is the mass defect. The corresponding energy difference is, so we're going to use the formula 9 times 10 raised to 10 kilojoule per gram multiplied to delta M. So this is the computed value of delta M here. Okay. Okay, so delta E is equal to 3.09 times 10 raised to 9 kilojoule per mole of lithium. So this energy is referred as the binding energy. It follows that, or it means that 3.09 times 10 raised to 9 kilojoule of energy should be absorbed to decompose 1 mole of lithium-6 nuclei into protons and neutrons. The binding energy of a nucleus, in a sense, is a measure of stability. The greater the binding energy, the more difficult it would be to decompose the nucleus into photons or protons and neutrons. So let's proceed with example number 4. For aluminum 28, calculate letter A, the mass defect, and letter B is the binding energy in kilojoule per mole. So let's first write the equation, okay, to compute for the mass defect. Okay, so aluminum 28, the atomic number, so again use the periodic table and the table for nuclear masses. The atomic number of aluminum is 13. So the atomic number is equal to the number of protons. So we have 13 protons here. Then 28 minus 13, so we have 15. So we have 15 neutrons. So 13 protons, then 15 neutrons. So make sure that the equation is balanced. So we have 28 here, 13 times 1, so we have 13, 15 times 1, so we have 15, 15 plus 13, so we have 28. 13 here, 13 times 1 is 13, 15 times 0 is 0, so 13 plus 0, still we have 13. So therefore the equation is balanced. So double check if whether your equation is balanced. So for the mass defect, so that is equal to 13. Then the nuclear mass of proton is 1.00728 grams plus 15 multiplied to the nuclear mass of neutron. Then minus nuclear mass of aluminum 28. So let's see aluminum 28. So where's aluminum? This one. Aluminum 28. Okay. So 27.97477. So delta M, or the mass defect, is equal to 0.24992 grams per mole of aluminum. So for letter B, for the binding energy, so we're going to use 9 times 10 raised to 10 kilojoule per gram multiplied to delta M. Then substitute the value of delta M here. So cancel the grams. So the unit will be in kilojoule per mole of aluminum. So the answer is 2.25 times 10 raised to 10. So that is for letter B. Okay. So next, let's proceed with fission and fusion. So nuclear fission and nuclear fusion are two types of nuclear reactions. Fission means to split and fusion means to combine. Therefore, in fission reaction, a heavy nucleus of atom is bombarded so that it splits, and in fusion reaction, two lighter nuclei are heated at high temperature so that they combine to form a heavy nucleus. Fission is the splitting of an atomic nucleus into two or more lighter nuclei accompanied by energy release. The original heavy atom is termed as the parent nucleus and the lighter nuclei are the daughter nuclei. So here are the examples of nuclear fission reaction. Fusion joins atomic nuclei together. The element formed has more neutrons or more protons than that of that starting material. For example, hydrogen and hydrogen can fuse to form a helium. So this one. Okay? So, here are the examples of fusion reactions. Okay? So, example number 5, calculate delta E in kilojoules per gram of reactants in a fusion reaction. So, this was for fusion reaction and then for fission reaction. So, let's proceed. Okay, so first, for fusion, solving delta E for fusion reaction. So, we have, okay, this one, we have 2 moles of hydrogen 2. Hydrogen 2, the nuclear mass of hydrogen 2 is 2.01355. Okay? So, for this one. So, for delta M, that is equal to nuclear mass of the product minus nuclear mass of the reactant. So, for the product side, we have helium-4. So, that is 4.00150 minus this one, the nuclear masses of hydrogen-2. So, the delta M for 2 moles of H2, hydrogen-2, that is equal to negative 0.0256 grams per 2 moles of hydrogen-2 because we have 2 hydrogen-2 here. So, solving for delta M for 1 gram of H2, okay, so we have negative 0.0256 gram per 2 moles. So, to cancel out 2 moles here, so we have, for 2 moles of hydrogen-2, we have 2.01355 grams. So, multiply by 2. Because for 1 mole, we have 2.01355. So, for 2 moles, multiply 2 here. Okay? So, 2 moles here will be cancelled out. So, okay, so the delta M for 1 gram of H2 will be equal to negative 0.006357 grams per 1 gram of H2. Okay? So for delta E, that is equal to 9 times 10 raised to 10 kilojoule per gram multiply to delta M. So substitute the delta M here for 1 gram of H2. So we have negative 0.006357 grams per 1 gram of H2. So cancel the gram here. So the answer is negative 5.72 times 10 raised to 8 kilojoule per 1 gram of H2 or hydrogen 2. So let's proceed with the fission reaction. So mass of the nuclear masses of the reactant side minus the nuclear masses of the nuclear masses of the product side minus the nuclear masses of the reactant side. So for strontium 90, we have strontium 90. Okay. We have 89.8869 here. Then next, we have for C144. Okay. We have 143.8817. Then, for neutron, so we have 1.00867. And for electron, we have we have 4 beta particle here. So, 4 times 0.00055. Okay? Then, minus, for U235, we have U235, this one, 234.9934. Okay. So we will get negative 0.21393 grams per 1 mole of U235. Okay? So, computing for the delta M for 1 gram of U235, so we have negative 0.21393 grams per 1 mole of U235. Then we have 1 mole of U235 here, and the nuclear mass of U235 is 234.9934 grams. Okay, so delta M for every 1 gram of U235 is negative 9.104 times 10 raised to negative 4 grams per 1 gram of U235. So computing for the binding energy, so this is the mass defect, okay? And this is the for delta E, we have 9 times 10 raised to 10 kilojoule per gram multiplied to negative 9.104 times 10 raised to negative 4 gram per 1 gram of U235. So the answer is negative or approximately equal to negative 8.19 times 10 raised to 7 kilojoule per 1 gram of U235. Okay, so let's proceed with the alpha particle emission example. Write the alpha decay equation for these 5 nuclides. Okay, so here's the answer. So the first step for alpha particle is to alpha particle emission is to write the alpha particle on the right side of the equation. Subtract 4 from the mass number here. So 256 minus 4, so we have 252 here. 2 minus 103, so that is 101. Then find the element with atomic number of 101 in the periodic table. So 101, so that is here, so that is mendelevium. Okay, so that is the answer for number 1. For number 2, we have 4 minus 231, so that is 227. 2 minus 91, so we have 89 here. So the element with atomic number of 89, so that is, okay, verse 89. So this one, so actinium. So that is the answer for number 2. Next, for number 3, we have 4 minus 225, so we have 221 here. Then 2 minus 89, so we have 87. And the element with atomic number of 87 is, where's 87? This one, so that is francium. So that is the answer for number 3. Number 4, we have uh, so this one, the helium or the alpha particle can be in any order. So you can write the alpha particle here or here. So it doesn't matter. So 4 minus 211, so that is 207. 2 minus 87, so that is 85. So the element with atomic number of 85, so that is astatine. So this one, astatine. So the periodic table of elements can be found on your canvas. Okay. So here, number 5, the last number for alpha particle emission example. So we have 4 minus 185, so that is 181. 2 minus 79, so we have 77. So the atomic number with 77, the element with atomic number of 77 is, okay, iridium. So that is for alpha particle emission or alpha decay. So remember that this one is the alpha particle. So next, let's proceed with beta particle. So write out the full beta decay equation. So for these 5. So here's the answer. So under beta particle emission, we have the beta particle here and the antineutrino here. 0 plus 0, so still, so this one is 6. Negative 1, so plus 1, because when you transfer negative 1 on the other side of the equation, so that will be positive 1. So 2 plus 1, so we have 3 here. So the element with uh, atomic number of 3, so that is the lithium. Okay, so let's verify. So this one is 3 lithium here. And next, we have this one, 0 plus 0, so we have 24 here, 24 here. Then negative 1 plus 11, so that is 12. So the element with atomic number of 12, so that is this one, magnesium. Okay. Next, problem number 3. We have 0 plus 0, so that is 201. Negative 1 plus 79, 1 plus 79, so we have 80. So the element with atomic number of 80 is mercury. Okay. Then next, number 4. So we have 52 here, 52. Then negative 1 plus 26, so we have 27. And the element with atomic number of 27 is cobalt. Then for the last number, we have 0, 0 here plus 42. So we have 42 here, 42 here. So that is balance. 0 plus negative 1, so negative 1, so we have 1 plus 19, so we have 20. The element with atomic number of 20 is calcium. So remember, under beta particle, we have electron here in the product side and an antineutrino. So you can check your answer by uh, adding the or finding the total of the mass number and the sum of the atomic number here. So they should be balanced. So let's proceed with okay. So that is for the mode of decay.